it.
Why entrepreneurs do so well? They just hire people that are good at different sections.
Right. Well, that's the thing. Like, you got to know what your strengths and weaknesses are in order to really determine where the help is needed the most. The next question is really just more of the same. So, and I forget where I got this from. It was definitely some online resource, but it was itemized based off of really, well, I'm just debating whether or not I want to go over this directly with you, because it's optimization with two constraints, but really, so let me take the star off. It's not anything really different, because what we're dealing with here is a plane and a paraboloid that intersect an ellipse. So we want to find the point on the ellipse that's closest to the origin, right? So we have two different constraints, but really, if you just follow the model, you're going to get the result. So yeah, I've made the decision. I'm going to put the star back on so that you could give it a try on your own first. I'd rather you give it a look, and then I'll take you through it, because if I do it the other way, then I'm taking all the thinking away from you and robbing you of that opportunity. So that's all right. But bottom line is, we have a set of rules that you just need to follow. All right, so what we're looking at here when we're dealing with two constraints is really nothing that much more complicated. Page 70, if you're looking. Conceptually, nothing much more complicated than the case involving the single constraint, except we're taking the sum of the scalars multiplied by their corresponding gradients. All right, so that's what we got to do. We have a plane and a paraboloid. They intersect an ellipse. We need to find the point on that ellipse closest to the origin. All right, so we can handle this a bunch of different ways, at least in the early goings, but we do have an idea of what our constraints are going to be. All right, because they're saying find the point on that ellipse. All right, the plane and the paraboloid intersect to form that ellipse, right? So basically, it's indirectly telling us that our constraints are these two functions, right? So what I want to do is rewrite them and set them equal to 0. All right, so we're looking at 12 minus, well, I'll do it the other way. That's just easier. X plus Y plus Z minus 12 equals 0. All right, and then X squared plus Y squared minus Z equals 0. All right, so two constraint functions. All right. What's that? 70? It's the previous one, yeah. All right, we're also going to need some representative of distance, because we're looking for the point on the ellipse that's closest to that, closest to the origin. So we'll have to handle that also. All right. So, but since we know that the intersection of the plane and the paraboloid is going to give us an ellipse, we know that those constraints are going to define the point in space. All right. So what I'm going to say is that we have some distance formula. Distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. All right. Now, it's distance between a point in space and the origin. So, zeros for my x1, y1, z1. And then we could just designate the other point to be, the other coordinate to be x, y, z. So x, some point floating out in space without restriction. All right, because the restrictions are naturally going to be held based off of the constraint functions. So I don't have to worry about them. All right, so that's my distance formula. But just to make life easier, because when you're, we did this with the distance from a point to a plane question, which is essentially what this is. We defined, instead of the distance d, we defined the distance as d squared, so that we didn't have to worry about the radicals. So x squared plus y squared plus z squared, and we called that some function f of x sub y, f of x comma y comma z. Okay, so, you know, just kind of, I'm zooming out so I can point out those rules again. I know they're teensy tiny now, but they should be the same size as your papers. So I have a need to find partials with respect to x, y, and z for my f function, then also my g function, and then the h function. All right, so I just need my g function and my h function, which I can get just by designating one of these as g of x, x, y, z, and the other as h of x, y, z. All right, so g of x, y, z is x plus y plus z minus 12, and h of x, y, z is x squared plus y squared minus z. All right, so we need all the partials for these. So we're going to need a total of 9 partials, 3 for each of them. All right, but you look at the quality of these expressions; they're not going to be hard to come up with. All right, I don't think I need my calculator out right now. I'll just put it away. I mean, I definitely don't need my calculator out. And I'm patched. All right, so we'll do that. Partial with respect to x, 2x. With respect to y, 2y. And partial with respect to z, 2z. For the second function, partial with respect to x, just a 1. With respect to y, also a 1. And with respect to z, a 1. H with respect to x, 2x. H with respect to y, 2y. H with respect to z, negative 1. All right, so we have all those partials. Now it's what we do with them that's going to matter. All right, because I already have my expression where g of x, y, z is set equal to 0. H of x, y, z is also set equal to 0, so that part's accounted for. Now I just have to set up my relationships, which is really just slapping a lambda onto each of the partials for g, slapping a mu onto each of the partials for h, and setting it equal to each of the partials, corresponding partials for x. All right, so I'd be looking at 2x is equal to lambda plus mu times 2x. All right, so we're just multiplying right on down the line, which is really not that bad. So, so lambda, 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 in red. Mu, mu, mu. 2y negative 1. All right, so these are the equations I need to solve in order to determine the x values that'll minimize my function. All right, those x values and y values and z values. All right, if there's more than one, we'll flesh it out in this process. And so we'll carry this out and see where it gets us. Really, it's just a matter of just trying to kind of find a path through the maze here. All right, and so since we have a common lambda in each case, the consideration might be to do something like, well, let's just set them all equal to lambda and see where that gets us. Another thing that we could do is to try to isolate a variable like x. If I isolate x, then I'll have an expression or an equation that's in terms of lambda and mu, and that could get pretty ugly pretty quickly. The last one here is actually the cleanest out of all of them, so maybe that's the way to go. So, there's a lot of different avenues that you take, but basically you're solving a system of equations. All right. So, and we don't want to forget that there's two other equations that are part of the action here. X plus y plus z minus 12 is equal to 0. And x squared plus y squared minus z equals 0. All right. So we have a total of 5 variables and 5 equations, which means somehow, some way, we're going to get our solution out of this. It just might not be pretty in all instances. All right. So looking at this one, for example, I see that I have really this amounts to a 2z equals mu minus lambda. So we'll use a brand new technique for this one called the right way. All right, so we had our setup. And I'll just recap it a little bit. We defined our plane, or they defined our plane for us. X plus y plus z equals 12, and the paraboloid z equals x squared plus y squared, and they intersect on an ellipse. But those end up being our two constraint functions. All right, so that defined for us f of x, y, z and g of x, y, z. All right. G of x, y, z and h of x, y, z. The function f was defined based off of the distance formula. But what we like to do, as opposed to using the square root version of it, is square the distance formula so that we still have a function of x, y, z, just not having to deal with the radical, because as the squared distance goes, so does the distance. All right, so if we can minimize the distance squared, then correspondingly we will have minimized the distance itself. All right, so we went through the process of finding all the partials, which was the easy part of all of this. And then we got to the part where we were defining our equations using lambda and mu. All right, and so that comes back to this idea where the product of lambda and our g partials, well, really our gradient vector value function multiplied by lambda for g, and our gradient vector value function in h multiplied by some constant mu, some constant multiple mu, added together would give us the gradient vector for f. All right, and so constraining it with g and h equal to 0 allows us to come up with, well, pretty much where we left off. Well, that's not true. We did a lot more after this, but I had to delete a little because it sucked. All right. So what we're going to do is solve, well, we could solve each of them for lambda. So we'd be looking at lambda is equal to 2x minus mu times 2x, and lambda would be equal to 2y minus mu times 2y. All right. The reason that's beneficial is because we can, now that we have lambda equal to something, we could set those two somethings equal to one another. All right, so we get a little highlighter action going on here. These two bad boys set equal. All right, so we're looking at 2x minus mu times 2x equals 2y minus mu times 2y. All right, left-hand side we have a common 2x that can be factored out, leaving us with a 1 minus mu. On the right we have a 2y that could be factored out, which leaves us with a 1 minus mu. Common 1 minus mu on both sides of the equation becomes irrelevant to the equation. We also have a common 2, so we can kill those also. So a lot of things that we can wipe out here, leaving us with just x equals y. All right, so we have a relationship where y and x are equal to one another. And that kind of sends us off to the races here, because I could do the same thing using x and z or y and z, right? Because if I took the z equation, what I would do is I'd solve it for lambda, right? I could get it as lambda in terms of z, but you know, what is that going to do for us? Because when I make a substitution, there's no x, there's no y in there, so it's not going to be as beneficial. But what I can now do is look at my two other equations where I had two equations in 3 variables. Now I could look at it as 2 equations in 2 variables, because I could replace all my y's with x's. All right, so I'd be looking at x plus z minus 12 equals 0, and x squared plus x squared instead of y squared minus z equals 0. 2 equations, 2 variables, I'll be able to get a solution. All right, so 2x plus z minus 12 equals 0. 2x squared minus z equals 0. Leave a little space there, because what I can do is I can add my 2 equations together. It's the elimination method, except I have a power of 2. Flow, but yeah, good call. So 2x squared plus 2x minus 12 equals 0. Knock off the 2, so x squared plus x, what the hell is that? Minus 6 equals 0. Coming from the other side? All right, so at this point, you know, pick your favorite method for solving a quadratic. Still here, it's brutal. It's like grating. All right, so if it's going to be factorable, we're looking at 3 and 2, most likely. So positive 3, negative 2. All right, 3 times negative 2 gives us a negative 6. 3 minus 2 is equal to 1, so that's good. So we're looking at x equals negative 3 or x equals 2. All right. Now this technique of Lagrange multipliers is for finding extreme values. So those extreme values could be max values or min values, right? So this could be the x value, a set of x values that lead to the shortest distance or the longest distance. All right, so we have to kind of flesh this out. Now I do know that y and x are the same, so y, if x is negative 3, y has to be negative 3. If x is 2, then y has to be equal to 2. So then I just have to figure out what z would have to be in order for this to play out. And, you know, minor adjustment on this bad boy right here. I'll just add the 12 and subtract the 2, x, and we'll get z equals 12 minus 2x. All right, so it's just a matter of plugging in a negative 3. So 12 minus 2 times negative 3, so 12 plus 6 is going to be 18. Or 12 minus 2 times 2, so 12 minus 4 is 8. So our possibilities would be the ordered triple, negative 3, 18, or 2, 2, 8. Now, ultimately, we're looking for the shortest distance. All right, so this is just an ordered triple. And it doesn't tell me anything about distance. What I want to do is go back to my distance formula, which is identified right up on over here. Well, we got several different variations of it, but this is the one I want. I'm going to go with a different color highlighter. All right. So, well, actually, that's not true. I mean, that's our function. It's really this one I want. And by extension, this. All right. So, long story short, well, I just kind of blasted through that. Distance is going to be equal to the square root of the squared values added together. So negative 3 squared plus negative 3 squared plus 18 squared. All right, now you just kind of use common sense here. There's no way that's going to give us a shorter distance from the origin than 228. So we can just ditch that one. I mean, it's already 18 units below the x-axis. I'm sorry, below the xy plane. So that one's not going to fly. So then we try the other one, which is 2 squared plus 2 squared plus 8 squared. And so we're looking at 4 plus 64. So root 72. 72. So you simplify if you want, but whatever, I guarantee that whatever the other one ends up giving you is not gonna end up being a good one. So this would be the shortest distance. All right. Oh, look at that, still far away. Find the point on the ellipse closest to the origin. All right, so ultimately we still needed the point. So the point itself, so let me not box that. So therefore the coordinate 228. That's the one that would be the final answer. All right, so ton of algebra here. And really, if you think about it, you know, I like to do this whenever I do applications of calculus, whether it's related rates in Calc 1 or, you know, volumes of revolution, applications in Calc 2, or something like this. I like to point out where the calculus happened. I mean, everything's a rate of change or relationship between rates, so it's all embedded there. But the act of finding a derivative happened very early on, and the rest was algebra after that. All right, which I showed you the wrong way to do it last time, and bearing in mind that the wrong way still would have gotten us, assuming I didn't. I mean, there was a lot of stuff that I wrote, but assuming that I didn't make a mistake in there somewhere, that wrong way still would have gotten the right answer. No right answer. It's just a matter of perseverance. But really, it's just these partials here. That was all the calculus. Everything after that was just solving equations. All right, so It's definitely something to get used to, but it's managed.